after J.J. Thomson's discovery of the electron and the proposal of the plum pudding model, the next major development in our understanding of the structure of the atom can be attributed to experiments done by Rutherford. Okay, Ernest Rutherford bombarded a gold foil by alpha particles obtained from a radioactive material. So if you have a very thin piece of metal, like your aluminum foil, so you have a gold foil there. Okay, what he did was he fired alpha particles at that piece of metal. What's an alpha particle? It's something that comes from a radioactive material. Okay, so if you have a radioactive material, okay, and you were to separate, so let me just do it here. So let's say you have a radioactive material here, so radiation comes out of it, right? So everywhere, okay. Take a little bit of that part of that radiation, okay, just a little bit of that radiation, and then what you do is you subject it to electrically charged plates. What is found is that this radiation would split into three typically. So one part would just go straight through, and that's called a gamma ray. So this is a symbol for gamma, Greek letter gamma. Okay. And then one part of the radiation would be attracted to the positively charged plate, would be deflected towards it. So that one part of the radiation would go this way. Okay. So that suggests it's made up of negatively charged particles. So this is called your beta ray. So Greek letter for beta is written that way. And we now know, in fact, that these beta rays are just high energy electrons. So that's why they're attracted to the positively charged plate, and they're deflected a lot, suggesting that the masses of these particles are very small. And down here towards the negatively charged plate, there's a slight deflection also. Okay, and those particles that are deflected that way are known as the alpha particles. So what you have here is your alpha ray. Okay, so alpha, that's how you write alpha in Greek. So you have your alpha ray. Okay, and so these alpha particles are positively charged particles, because they're attracted to the negatively charged plate. They're not deflected as much because they're much heavier than the electrons, so not as much as the electrons. And we now know, in fact, that these are just helium ions with a positive 2 charge. So imagine each helium atom stripped of its electrons. That gives you an alpha particle. Okay, so alpha particles are fast-moving helium ions. Now, what were the results of Rutherford's experiment? So he fired alpha particles at a foil of atoms, and what happens was most of them just pass through with very minor deflection. That's what you would expect for the plum pudding model. All the particles would just pass through with very minor deflection. But one strange thing happened in this experiment, in that a small fraction were actually scattered at large angles and backscattered. So not all, just most of the alpha particles went through. If the plum pudding model were correct, they expected all of the alpha particles to pass through with minimal deflection. And most of them did, but what happened was this: you have this small fraction that were actually scattered at large angles, and there are some that were even backscattered. So large angle scattering means that instead of going straight through or with very minor deflection, you see some of these B alpha particles deflected at very large angles. So this would be your large angle deflection, you might say. And occasionally they'd even see something that gets backscattered. And Rutherford described this observation as though he fired a shell at a piece of tissue paper and it bounced right back at you. Okay? So anyway, the conclusion from these experiments of Rutherford was that the mass of the atom is concentrated in a tiny nucleus, and that tiny nucleus is positively charged to account for the large angle deflection and the backscattering. Okay, now electrons move around the nucleus, and the diameter of the region where the electrons roam is at least 10,000 times that of the nucleus. Okay, so this diagram should illustrate more or less why that those conclusions can be made from Rutherford's experiment. Okay, so if you have alpha particles, let's say these red particles here are alpha particles, and you have your this is your nuclear model of the atom. How would this model, so it's a series of, it's just a collection of atoms with very tiny nuclei and mostly empty space around them. How would this explain Rutherford's experiment? Well, if most of your particles, if it's mostly empty space, so this is at least 10,000 times bigger than its individual nucleus, then most of your particles will just pass through with a minor deflection like particle B right here. Okay, so this would be your typical trajectory. Okay. However, if you have a particle that's whose trajectory is almost head-on, puts it on almost head-on collision with a nucleus. Remember, your nucleus is positive, right? So if it's almost a head-on collision with the nucleus, then this is where you would see backscattering. This is how you would explain backscattering. Okay, there has to be a very strong repulsion, so that suggests that whatever it's colliding with must be positive, because your alpha particles are known to be positive. Okay, and C right here, it would be representative of an alpha particle that would be deflected at large angles. So it's got this what we call glancing collision, just slightly off to the side of a positively charged nucleus, so it will be repelled strongly, so it will be deflected at a large angle. So this would be your large angle deflection.